So I started recording. That's a good step. And we got a fair bit to go, so we're just going to jump right into it. And I'm going to share my screen, and we're going to do some of these drawing things. So if you do have questions during this, make sure to speak up, because I won't necessarily see you. I only see a few of you on the side of my screen, not everybody here. Now, I do notice two of you close together from different families not wearing masks. I hope you do not sicken anyone you care about.
4-day sleepover.
And so the process for ray tracing from lenses is really, really similar to what we had in mirrors. And so I actually copied and pasted the 3 rays that we had from before, and I only had to change them just a little bit. So we're going to have 3 rays that we can trace through lenses. One big thing, obviously, is that the light rays do go through the lenses rather than bouncing off of them. But otherwise, the language is really, really similar. So the first ray we're going to draw is going to be, let's see, get my line here, is going to be from all of them will be from the top of the object. And this will be parallel to the optical axis. When it hits the lens, now it's going to go through the positive focal point. So positive means where the light will actually go. Negative will mean where the light wouldn't technically go. So the negative is on the left. It's closer to the object. The positive is on the right. Usually you'll just see these labeled as F on the F and F. I've only made that distinction so for the language that we're using up here. So I'm going to take my ray, and the first one gets refracted, which means bent, through the positive focal point, which is over there. It's going to go continue through, like so. And I'm going to change those to red for consistency. Oh, I guess those are all the same. So, like so. Second one, which I'll make as green, goes from the top of the object through the negative focal point. And once it hits the lens, it is refracted so that it goes parallel to the optical axis. So these two are really similar to the first couple of rays that we saw in going with the mirror. So it goes through that focal point, best I can, hits the lens, and then from there, parallel. We can see already where the image is likely to form. And then the third ray will go from the top of our object through the middle point, so right through where the optical axis intersects the lens, and continue through unchanged. So that's very similar to being reflected at the same angle. That'll be our blue. And that defines where the top of our image is going to be. And then, of course, if we were to scan down our object, the image would also just move closer and closer to the optical axis. So essentially, we have the same thing here. It's going to be flipped. It's going to be a bit smaller. Like so. And I'm going to move that just a little bit so it matches up well, like so. And because I did everything in scale on this diagram, I can actually measure that distance as well. So I'm going to measure from the point that it meets the optical axis back to center of the lens, and I get an image distance of 37.11 meters here. Millimeters, I should say. And so if we have time, we'll go back and check that with the math and make sure that that works out. But it should be really, really close. Okay, so ray tracing is going to be actually very, very similar. We could also measure the relative heights of these two and find out their magnification based on how tall the object was and how tall the image is. Well, let's go on down to, so are we good to go on to another one? I guess I can expand this too, and so I can see all of you. Why can't, okay, there we go. Okay, and I did remember to record this, so if you need a little extra, you can go back.
Mr. Skonika, would the image be flipped right to left or no?
Good idea to, let's talk about what this will look like. One thing we can definitely tell from this is that it's inverted. It's demagnified, meaning smaller. As part of this inversion, we can also, this is not, we are looking in one, or in 2 dimensions, but this is rotationally symmetric. So since it flipped from top to bottom, it would also flip from left to right. So let's say that it's inverted, so upside down and left to right. It's demagnified, meaning that it's going to be smaller, and that'll be the case for any of these that we have with the focal length smaller than the object distance, and we'll try something with those two flipped. Is this a real or a virtual image? Are the light rays actually coming together there in real space? And how can we tell?
I think it's real because it's on the side of positive F rather than negative F.
Right.
Meaning that the light rays went through the lens rather than being sent back.
Yep. So in a mirror, of course, the real side is where the light rays would be reflected to, which would be still on the same side as the object. But here in a lens, the light rays go through the lens. And so if they do meet someplace over on the right, it's going to be a real image. Wunderbar. Okay. Now, let's apply the same rules to the same setup, but with a concave lens. The difference with a concave, of course, a convex looks like this, but a concave, I can't quite do it with my fingers, looks the other way, like an hourglass. Oh, I should say, this is how we symbolize a thin lens. So instead of having to be careful about making the curve correctly like we did with a mirror, we just put a line and a convex lens to illustrate that it's coming to a point and then getting wider in the middle and coming to a point at the bottom. We use arrows pointing away at the top and bottom. The concave lens, which looks more like an hourglass, wider at the top and bottom, skinny in the middle, we draw again with a straight line, but then the top and bottom are inward pointing arrows. This works just for thin lenses where the radius of the lens is a lot larger than the thickness of the lens, but it works really, really nicely. So from this concave lens, the only thing we have to change is where the positive and negative are. Because they're curved in an opposite way, the positive is actually on the left, the negative is on the right. But then our rules are applied in the exact same fashion. So our first ray goes parallel. Now, this is a diverging ray. It doesn't go through the negative, it actually goes through the positive, but of course we know that it doesn't reflect there. So this is a trick that we say, we go in and we say, from the center, let me see if it'll let me select. From the positive focal point and then through where it intersects at the mirror, or at the lens. And then I'm going to shorten this up like so. like that. Goes away from the positive, or as though it were originating at the positive. Second line, instead of going through the negative, well, it does aim for the negative. Let's see if I can go, so from the top, as though it were going to go through the negative, but instead, when it gets to the lens, it refracts parallel to the optical axis. Like that. And the third one, as usual, is the easy one, because if it goes through the center of the lens, either type of lens, it continues on straight. Oops. Now we can see what we were looking at the other day, that this is a bit of a problem because these rays don't ever intersect. They diverge from each other. So just like we did with the mirrors, we would actually trace them back into the virtual side, trace the refracted rays back. So let's see if I can grab each of these. I'm going to make them dashed to show that they are in fact virtual rays. And then the dashed blue line would just go over where the blue line is. So these meet on the left-hand side of our lens. We can measure the distance again, just so if we get to it, we can make that calculation. Shoot. I get 19.28. Okay, and let's make our list with this. Okay, what we can tell, a couple things are, this is a much smaller image, so the image is demagnified. Meaning it's smaller. It is upright, meaning it looks normal. Is it real or is it virtual?
Virtual.
Virtual. Those rays don't actually meet. So we couldn't put it in put it onto a screen. This is a useful type of lens, like I mentioned yesterday, in that a lot of us, if we're nearsighted, that's the general shape of the lens that is in our eyeglasses, or even in contacts, although they take the shape where one side is concave, the other is convex, but overall it still works like a concave lens, diverging rays. Okay, good. We got one more condition I want to share with you. Our last condition down here uses a convex lens again, but this time the object is inside the focal length. So in this case, I have it as 26.89 millimeters. That's just where it got stuck. We're going to apply the same rules as above, but in this case, we'll also have to modify it a little to account for where everything is. So our first ray goes into the parallel to the optical axis, and then from there, straight through the positive focal point. Our second one goes from the top of the object through the negative focal point, which we can't really get to, so we're going to have to, as before, originate from the negative focal point, go through the top, and then it'll hit this lens. So I realize now I have to make this lens much bigger to accommodate that. So I'm going to make it up like that, just so I know where that plane is. I'll have to zoom in to get the middle. But now it'll go through the same point as before, and a ray that does this gets refracted so that it goes parallel to the optical axis. It's our green ray. And then the easy one, oh, and I'm going to shorten that up. Let's put another line back that way just so we know. That didn't quite work out. Parallel. Shoot. Try it again. That's there, and then I'm going to put that as dashed because it's not a real thing, but it is an important one to keep track of. Okay, and then our final one is again the easy one, going from the top of our object through the center of the lens where it hits the optical axis. We'll make that blue. And I've made this, this really should be centered again. I can do that easy. We're going through still working with the center of this lens. I just had to make the lens big enough to accommodate all of my rays. And we see again over on the right-hand side, these are not converging into an image. So let's extend them backwards. What did I do with that? That's what was wrong. Oh heavens, that's going to cause problems. I've got to redraw that one because that one did not turn out with the multiple parts. Like that, and there. I'll just make that green and we'll call it good. There we go. So now let's extend our refracted rays straight back the way they came, the way they were bent. So each of these we're going to extend back. Of course, this one is going to be in the same angle. It's going backwards, so I'm just going to copy it, plop it right here, and make it dashed. The green one will go straight to the left from this point. And the red one will go straight back from this point, following the line. And I have found in my years of doing this that the lenses work out better than the mirrors did. And I always thought that that was probably mostly because we're better. This is a straight line, so it's easy to draw and easy to measure. And the curve of the mirrors always makes it a little more challenging. But we can see pretty easily where our image is going to form, where those lines cross. Extend this down. Make it a bit bigger. And there's our image. So I'm going to measure this one once more, where our image goes. Shoot. Looks like 55.93 millimeters. Was it 3.3? So looking at this, the image is in the same direction as the object, so it's upright. It's way bigger. Is it virtual or real?
Hello. Hey, Barbara. I'm good. How about yourself?
Virtual?
How do you know?
It's on the same side of the lens as the original object. It
Right.
didn't like go, the light didn't go through the lens and then
Bingo.
meet.
Kind of a bummer that she doesn't
Yep.
get to, hang out with friends.
Couldn't actually put a screen there to capture it for the exact reason Noah was telling us.
We're entertaining too.
This is still a really useful tool. Most of you have used it. This is how a magnifying glass works. You put the object inside the lens's focal point, and it makes a much bigger magnified but upright image beyond it. So it seems a lot bigger. Let's quickly, since we still got a few minutes, let's do the math on this and just see if all of these work out. So I'm going to be able to keep this on my board, on my screen, and refer back to it, but I'm going to switch over to my iPad so we can do these calculations quick. I got to do this.
It doesn't have to be the bridge, does it? Okay.
Okay, so I'm just going to call this lens calculations. And what we found, some people's worked out better than others. This is a challenging way to do our labs, but the last lab had you presented a way that you could actually find the thin lens calculation. Most of you did. For thin lenses, again, we found something just like the mirror. 1 over f is equal to 1 over di plus 1 over do. Things we have to keep in mind is that for a convex lens, same as a concave mirror, let's do this. F is positive. For a concave lens or a convex mirror, F is negative. But otherwise they work the same. So doing the, I lied, I can't see that. Doing the measurements that we had before, going back to our first one, we had a focal length of 25 millimeters, an object distance of 79.37 millimeters, and that's a weird number because I just threw it out there and then measured it. Let's find the image distance. So we know 1 over F is equal to 1 over DO plus 1 over DI. I prefer to just put the numbers in and then I do the math all together. So we'd have 1 over 25 millimeters is equal to 1 over 79.37 millimeters plus our unknown. When I do this, then I'm going to take the 1 over, and I just put it in my calculator like that. 1 divided by 25, I'll subtract the 1 divided by 79.37, and I get 0.027. For the units would be millimeters to -1 because it's 1 over millimeters. That's equal to 1 over DI. And then I'm just going to flip that. So I'm going to use the x to the -1 button on my calculator here to just flip that answer. And I get 36.5. 50 millimeters is equal to DI. Checking back at my measured value, pretty close. Measured 37.11 millimeters. Probably doing it quickly like that, I goofed up just a little bit on an angle, and that happens. The lines click to it. If we go down to example 2, the only difference was we had focal length now of -25 millimeters. In this formula, we'd usually say at a 25 millimeter concave lens, but it's negative for our formula. The object distance is 79.37 millimeters. We set it up in the exact same way. So it's -1 over 25 millimeters. So I'm going to take -1 over 25 minus 1 divided by 79.37. I get -0.0526 millimeters to the -1, and that's equal to 1 over DI. And so the image distance is negative, as -19.01 millimeters. And I measured, and it was -19.28 millimeters. So again, a very close one, probably a little different based on how quickly I'm making the measurements. And our last example, and now we're bumping into the time here. We had a focal length. I put it at 50 millimeters. An object distance of 26.89, because I just plopped it down there. And this is the one where the object was inside the focal length, obviously. We treat it the same way. 1 over 50 millimeters is equal to 1 over 26.89 millimeters plus 1 over DI. So I'll subtract 1 over 50 minus 1 over 26.89. And I get, again, a negative, of course, negative 0.01719 millimeters to the -1, and that's 1 over DI. Flip it over, and I get negative 58.18 millimeters. And I measured -59.33. So again, close, but with quick measurement, that could be improved, could probably do better. If you want to find the magnification, magnification is going to be the same as the mirror as well. Negative DI over DO will tell you the magnification, and you can find the size based on that. Whew. And that's it, all of physics.
Correct.
So we've got a few more
Almost
days.
at the finish.
Almost the finish line. You've got the one assignment that is based on this. I am happy to answer questions if you want to hang on here, or if you want to jump in tomorrow through Friday in any of the office hours, you are welcome, or to shoot me an email if you have a question. Look forward to hearing from you. If we don't see each other again, have a good summer. Stay away from each other. Sorry, you can't tell because I'm looking